Welcome to the massive open online course on Aspen Plus. In today's lecture, we shall perform some practice problems for pure component analysis. It is about property methods and property estimations. So we have total 6 problems that we will solve today. The first problem is about property estimation of user-defined vanillin and ibuprofen. Now, both vanillin and ibuprofen are common components, so they are available as conventional components in Aspen database. But in today's problem, we will use them as user-defined. So for that, we will use unifact property method as it has been asked in the problem. So for that, let us go to the Aspen Plus simulation window. Here we have to set the component as user defined. So let us say my component is Vanny. We place them as alias, save, alias also Vanny. Press next. Here we have to draw or import or edit structure. Now for that, we do not know the structure of vanillin. So we can go to internet and search for the structure. So we write vanillin over here. And we find the structure. So here we have all the necessary information for vanillin. We have molecular weight, boiling point, density, etc. So this is the structure that we have, which we want to draw. So we have one benzene ring, one oxygen over here, H, the OH, O and CH3. So we will reproduce it. So we have a benzene ring, then we have a C, we have an O here, and then H, and then again another O, and here also we have an O, and there is a CH3 over here. So all of them are single bond except this one, which is double bond. So let us connect them. So this one connect, these two are connected, these two are connected, these two are connected, these two are connected, and these two will be connected with a double bond. So that will make our structure same as the vanillin structure. Okay. So we can close it. The structure is now available because we have drawn it. And molecular weight, it is 152.15. So 152.15. The normal boiling point is 285 degrees centigrade. And the specific gravity, what is the density? It is 1.06. So this is the specific gravity. Press next. We do not have any additional data or parameters, so we can just ask the Aspen to estimate the property and finish. Similarly, we look for ibuprofen. Let us name it as ibupro. The alias also we give the same name. Press next. Now here also we have to draw the structure or import. Now we do not want to do the same exercise again and again of drawing structure. Rather, we can search for a molecular structure in the internet and download it. So for that, we will go to internet once again and look for, there is a website called Chemical Book. You can even directly go to that website, Chemical Book. So it is chemicalbook.com. Here you can search for the structure ibuprofen, and here you have the structure in .mol file which you can download, and you can see this file has been downloaded. It's a .mol file, so it contains the molecular structure of ibuprofen. So it is available. Now go back and just open that particular structure, bring it over here, and this is available with you. Close it. You have to give the molecular weight. So again, you search for ibuprofen. I think it will be available in Wikipedia. Yes, it is available. 206.29. So just write 206.29. Boiling point, it is 157. And specific gravity, it's not given, but just you can enter Wikipedia. I believe it will be available over here. Yes, the density is available. It is 1.03. So just write 1.03. Press next. Here again, we do not have any more data, so we just estimate the property. Finish. Now both the components are defined. Now press next. And we have been asked to use the unifac property method, so we just write unifac. Run. Yeah. So it's available now. The data is available over here. Just go to the results. Yeah. So the critical temperature of vanillin, it has estimated to be 812.848. Okay. So let us check what is the critical temperature of vanillin. So again, we go to the internet and write critical temperature. So critical temperature of vanillin is, so here it is available, vanillin thermodynamic and transport properties. We have critical temperature 777 Kelvin, whereas Aspen property estimation process, it has calculated the critical temperature of vanillin as 812. So obviously the estimation is always a rough calculation, so it will not give the exact experimentally found value, but it has estimated some value of critical temperature, which we can always use if the component in question is not available in the conventional list of component in Aspen Plus database. Here we have certain temperature dependent properties of vanillin: heat of vaporization, liquid thermal conductivity, etc. has been found. And for ibuprofen, the same thing. Heat of vaporization is this, liquid thermal conductivity, they are all available. And for pure component case, ibuprofen, the critical temperature has been calculated to be 623.705, and you can just go and check in the internet what is the actual critical temperature of ibuprofen. That can be taken as a task, and you can just check how close they are. The next problem that we have is about verifying whether enthalpy of toluene is affected with the change in pressure from 1 bar to 20 bar. And the temperature range is minus 50 degrees centigrade to 150 degrees centigrade, and we have been asked to use predictive SRK property method. So it's a new simulation. So open a new simulation. Here you have to add toluene and then press next, and you have to choose the property method, which is predictive SRK. So it is PSRK. Run. Okay, so the estimation has been done. Now we have to bring in the pure, and it is about the enthalpy of toluene. So just bring in enthalpy, which is H, enthalpy of a pure component in joules per kilomole. Write vapor and liquid both. It is from -50 to 150 degrees centigrade. And the pressure is 1 bar. Okay. So everything has been given. -50 to 150, 1 bar. Okay. -50 to 150, 1 bar. Right. So now we have to run analysis. Okay. So it is available, the vapor H toluene and liquid H toluene. So we just write it as 1 bar, and this one also we write 1 bar, because both the graphs are for 1 bar pressure. Now the same exercise we have to do for 20 bar also. So we bring another pure component exercise. There also we have to choose the enthalpy, which is here. Press toluene, -50 to +150, and then here we have to write 20 bar. Okay, everything has been given. Now run analysis. The second case, we convert it into joules per kilomole, and we change it to 20 bar and 20 bar again. Okay. Now we merge these two plots so that we can understand them better. Yes, we have merged, but we have to use it with a single y-axis. Yes. Now you can compare them. You can see that the vapor curves, that is the blue one and red one, they are quite apart. But the liquid curve, they are superimposing on each other for 1 bar and 20 bar. That necessarily means that in liquid phase, the enthalpy doesn't change with pressure, but in vapor phase, definitely the enthalpy changes with pressure. So our next example is about finding the boiling point of N-butane at 1 bar and 10 bar by equating the Gibbs free energies of vapor and liquid phases. So as we know that if the Gibbs free energy changes like this in vapor phase and it changes like this in liquid phase, then the point of intersection where the Gibbs free energy in liquid phase and Gibbs free energy in vapor phase will be equal, actually that is the boiling point of the pure liquid. So that is about theoretical understanding. So in this manner, we shall find out the boiling point of pure N-butane at 1 bar pressure and at 10 bar pressure. So we open a new simulation window. Okay, so we have to enter N-butane and the property method, we will take PRBM, that is Peng-Robinson equation of state with Boston-Mathias modifications, and we will run it. Yeah, so it is run. Now we have to find the Gibbs free energies for vapor and liquid phases. So we call the pure analysis tool the Gibbs energy for pure component in joules per kilomole. Take both vapor and liquid, select butane, make it 1 bar pressure, and begin from -50 to say 150 and run the analysis. Yes, so this is the temperature at which the Gibbs free energy for vapor and Gibbs free energy for liquid, they match. So let us zoom it a bit. Okay, so zoom it once again. Okay. Yeah. So we can see it is -0.8 degrees centigrade. This is -0.8 degrees centigrade, or between -1 and -0.8, we can say -0.9 or -0.85. So we conclude that at 1 bar pressure, the boiling point of N-butane is -0.85 degrees centigrade. Now we have to cross-check with the actual value. So let us again go to internet and write here boiling point of N-butane it is -1 degree centigrade. Okay, so the normal boiling point is -1 degree centigrade, and we have found it -0.85 degrees centigrade. But you also have to remember that we have taken it 1 bar, not 1 atmosphere pressure, and 1 bar is less than 1 atmosphere pressure, because 1 atmosphere pressure means 1.0125 bar. So this much of error is expected. Now the same thing we can do it for 20 bar as well, and run the analysis once again. And here we find it over here. Okay. So it is somewhere 114 degrees centigrade. So at that temperature, the Gibbs free energy of vapor and liquid, they intersect, the lines intersect with each other at 20 bar pressure. So we can conclude that at 20 bar pressure, the boiling point of N-butane is 114 degrees centigrade. So our next problem is comparing the enthalpy of vaporization of methanol through pure analysis and compare with NIST experimental data set. And we can use unifact property method. So for that, let us go to the Aspen simulation window once again. Open a new simulation. So it is methanol and enthalpy of vaporization. So methanol we use unifact property method. Run it. Done. Now you have to bring in the pure analysis. So it is enthalpy of vaporization. So you will find it as DHVL. This is enthalpy of vaporization of pure component, joules per kilomole, methanol. Okay, this analysis we'll do later. First, let us bring in the NIST data. So NIST data for methanol, let us bring it first. So it downloads through internet, so it might take some time. It all depends upon the speed of internet. Somehow today it is quite slow. Yeah, now it is available. So just close it. And here you will find enthalpy of vaporization or sublimation, liquid versus gas. Here you find the experimental data, and there are actually 59 sets of data, and most of them are accepted. A few are rejected as well. So we save the data and we save only the accepted data. So press OK and you will find a data set over here. So go to the data set. You'll find the property and methanol. This is the data. And you can compare this data with the property estimation run of Aspen Plus. But first, let us plot them, property versus temperature. So these are the experimental data that we have found. Okay. So DHVL in joules per kilomole with temperature K. Fair enough. So it begins from around 245 Kelvin to 480 Kelvin. So let us run our simulation in this window. So 245 Kelvin to 480 Kelvin and run analysis. Yes. So it is joules per kilomole, temperature in Kelvin. So it's also the same. So now let us compare the graph. Merge the plot. Yes. So you just make it a single axis graph. So that's it. So here we find the result. We have the experimental result, all green dots, and we have the simulation result, the blue line, and both of them match. That means the Aspen property estimation method, namely unifact property method, it can properly estimate the enthalpy of vaporization of methanol, and it can match the data found through NIST database. So our next problem is comparison of Peng-Robinson method and the steam table method, these two property methods in verifying the entropy of water at 0 degrees centigrade and 800 degrees centigrade at 500 atmosphere pressure. So for that, let us open a new simulation window. Here we find water, and we have two estimation method. One is Peng-Robinson method, which is equation of state method, and we also have the IAPWS 95, which is steam table method, which is actually, it is ideal for water and steam. So we use IAPWS. We run it. We have to run twice because we have two property methods. Yes, now it is done. Now we have to verify the entropy of water at 0 degree and 800 degree centigrade. So just bring in the pure analysis for water, and entropy is represented by S, entropy of a pure component, units joules per kilomole K. Write both vapor and liquid, and there are two values. One is 0 degree centigrade, another is 800 degree centigrade. And the pressure is 500 atmosphere. It is 500 atmosphere. Okay. Now run analysis. First, we will use the steam table method. We have two property methods over here. Okay, so we are not interested to know about the plot. We will see the result only. So this is the result. We have two temperatures, and the pressure is 500 atmosphere, and we have the vapor entropy and liquid entropy. We have to bring in the pure component once again because we have to do the same thing with Peng-Robinson method. So bring in the entropy, sorry, it is entropy for vapor and liquid. Select water, a list of values, 0 degree centigrade and 800 degree centigrade. Pressure is again, it is 500 atmosphere. Okay, now you have to run analysis. So here again, you see this one, 500 atmosphere for pure input, and this one you check. So this is pure 1, this is pure 2, this is for steam table method, and this is for Peng-Robinson method. Check the results for both. Okay, so here you can check the, in steam table method we have, let us use it as, let us take kilojoule per kilomole K. The figures will look better. Here also take kilojoules per K. Yeah. So in Peng-Robinson method, we have 53.3176. And in steam table method, we have 52.4944. Now, as it is steam table method, at 800 degrees centigrade, it is gas. So I believe this figure is correct. It is 52.4944. And at 0 degrees centigrade, it is liquid, mostly, if it is not solid. So it is minus 169. In Peng-Robinson method, it is calculating minus 175.72. Obviously, it cannot, because it's an equation of state method in gas phase, so it will not predict the liquid phase behavior properly. But vapor phase, it has predicted well, because it is minus 53 and here it is minus 52.5. So which are very close enough. So we can conclude that Peng-Robinson method can very well predict the entropy of water in the vapor phase. So in the last problem, we have to find the vapor pressure of methanol in temperature range of 10 degrees centigrade to 200 degrees centigrade and find its boiling point at 30 atmosphere vapor pressure. That means when the vapor pressure is 30 atmosphere, what is the boiling point, that we have to find out. And we have to use Peng-Robinson property method. So again, go to the Aspen Plus simulation window and open a new window, add methanol and Peng-Robinson property method. Run. Okay, so this is the last example of pure component where we have to find the vapor pressure. So vapor pressure is represented by PL, pure liquid. So liquid vapor pressure for a pure component calculated by the specified property method, and for us in this example it is Peng-Robinson method. Let us use atmosphere over here, because we have 30 atmosphere we have to calculate, and it is 10 degrees centigrade to 200 degrees centigrade. So write 10 degree to 200 degrees centigrade. Choose methanol and we are set. Now run the analysis. Yes, so this is the vapor pressure curve for pure methanol with respect to temperature. So now you can check at 30 atmosphere, the temperature is 185 degrees centigrade. So basically, if you hover around it, you can check the value. It is 30.2 atmosphere and 185 degrees centigrade. So actually at 30 degree it should be a little less, maybe instead of 185 degrees centigrade it can be 184 or 183.5, not less than that. So we can conclude that when the vapor pressure is 30 atmosphere, then the boiling point of methanol will be 185 degree centigrade. So in today's lecture, we have done various practice problems on pure component analysis. It is an extension of the property estimation methods that we have learned. So in the very beginning, we have learned each and every component individually, and today we have done some practice problems. So we end our lecture with these 6 problems only. We'll continue in the next lecture. Thank you.